Cavalieri's principle. Cavalieri's principle states that if two solids are the same height and the areas of their cross-sections are equal at every level, then the two solids will have the same volume. Let's actually show this with the triangular prism and rectangular prism that we have. We can clearly see that the height of each prism is the same, 6 and 6. So let's find the area of our base, which we use capital B for. In our triangular prism, it'll be 1/2 the base of the triangle, which is 10, and the height is 2. So we'll have 5 times 2, which is 10 square units for the area of our base. If we do the area of our base in our rectangular prism, it's going to be 5 times 2, which is also 10 square units. And if we find the volume of each, which is going to be area of the base times the height of the prism, we're going to have the 10 that we just found in this triangular prism times the height, which is 6 of the prism, and that gives us a volume of 60 cubic units. And if we do the volume over here, it's going to be area of our base, 10, times the height, 6, so it's also going to be 60 cubic units. So the area of the cross sections, the triangle to the left and the rectangle to the right, are equal in area at every single level. Therefore, these solids have the same volume. For an extension of this principle, let's go to the appendix. Here's an extension of Cavalieri's principle to the volume of a hemisphere and the volume of the section between a cone and a cylinder. And again, Cavalieri's principle states that if two solids are the same height and the areas of their cross-sections are equal at every level, then the two solids will have the same volume. So we have this cross-section right here. It's a circle, and the area of a circle is pi times the radius squared. Well, if we extend the radius out horizontally, we can also extend it out diagonally to meet with the edge of this cross-section, so the hypotenuse in this right triangle that's being created is the radius of our hemisphere. This height is the value h that's been assigned to it, and in order to solve for the radius of this cross-section, we would do this, I'll call it b squared plus h squared equals r squared. If we solve it for b, we will have that b squared is equal to r squared minus h squared, and then if we square root it, we see that this b value is the square root of r squared minus h squared. So that is the radius of our cross-section. And if we square that square root, the square root cancels out, and we are left with the area of the circle being equal to pi times the radius squared minus the height squared. Now let's look at the washer. The washer, we have a cylinder outside, and we have this cone on the inside. Therefore, the area of the washer being created between the cone and the cylinder will be equal to pi times the outer radius, which is equivalent to r, our original radius of the cylinder, squared, minus pi times our height squared. Like this distance height here is going to be equal to the radius of this, the inside of this washer. And this ends up being true because also the radius of the cylinder is going to end up being equal to the height of the cylinder as well, because this radius of the hemisphere is equal in all directions. So this radius is also going to be equal to the distance from this center point all the way down to this center point. That's going to also be our R value. So whatever height we choose to put the washer at, its height there will be equal to the radius that it produces for the intersection of the washer. That's how we get pi times r squared minus pi times h squared. We can factor a pi out of both terms, and we're left with pi times r squared minus h squared. Hey, wait a second. These are equivalent areas. So the area of the shaded region of the circle, shown here to the left, and the washer to the right are equal at the same level. Now, if we find the volume of the hemisphere, it ends up being half the volume of a sphere. And remember, the volume of a sphere is equal to 4/3 times pi times the radius cubed. Well, we can rewrite the volume of a sphere as being 2 times 2/3 pi r cubed. Like, you can rewrite 4/3 as 2 times 2/3. And that's what was done here. And then if you take half of 4/3, you just get 2/3 pi r cubed. So that's the volume of a hemisphere. Now let's look at the volume of the cylinder minus the volume of the cone. Remember, we had that cross section that we had to find the area of on the previous slide, and we showed that the two areas between the hemisphere cross section and this cross section were equal. So if we have the volume of a cylinder, that's going to be pi times the radius squared times the height. But remember, this radius from here to here is equivalent in the hemisphere, which also means if I extend it straight up, this is still the radius of the hemisphere, which is equivalent to the height of our cylinder. So therefore, we can substitute r in for h here and get pi times the radius squared times the radius again, which is pi times the radius cubed. That is the final volume of our cylinder. Now, if we have the volume of our cone, the full cone, we actually use that same principle. 1/3 pi times the radius squared of the circle times the height, which again was r. So that's going to be 1/3 times pi times the radius squared times another radius, because remember, the radius and the height of the cylinder and cone are equivalent. So we end up getting 1/3 times pi times the radius cubed. I'm going to rewrite that down a little lower so it doesn't cover. So we have, for the volume of the cone, 1/3 pi times the radius cubed. And then if we subtract these to find the shaded volume between the cylinder and the cone, we have pi r cubed minus 1/3 pi r cubed, which is 2/3 pi r cubed. So that is equivalent to the volume of the hemisphere. Which solid has the greatest volume? Is it this rectangular prism that has a length of 2 pi, a width of 8, and a height of 14? Is it this rectangular prism that has a length of 4 pi, a width of 4, and a height of 14? Or is it going to be this cylinder that has a radius of 4 and a height of 14? Well, let's actually find the volume of each one and then compare. So in this first one, the volume is equal to length 2 pi times the width 8 times the height 14. If we multiply 2 and 8 together, we end up getting 16, and 16 times 14 is 224, and we still have pi in our answer, and this is cubic units. Okay, now let's find the volume of this middle rectangular prism. So the volume here is going to be the length 4 pi times the width of 4 times the height of 14. Well, again, we're going to have 4 times 4 is 16, times 14 is 224, so we have 224 pi cubic units for our volume. Okay, now let's find the volume of the cylinder. The volume of a cylinder is pi times the radius 4 squared times 14. 4 squared is 16. 16 times 14 is 224, and we still have pi as a constant in our solution, and that is 224 pi cubic units for this volume. So all three of these volumes are equivalent or the same. So there is no solid that has the greatest volume. What we found when finding the volume of each of these three solids is that they are all equal to one another. The heights of the three solids are 14. The area of the cross sections were all equal. They were all 16 pi at every level in each of the three solids. Therefore, they all have equal volumes.